In our last lecture, we discussed the histogram equalization and the histogram modification approach towards image enhancement. Basically, there what we were doing, that from an image, we were constructing the histogram, that is an histogram which is defined fully over the image, and then from that histogram, we were doing a transformation, okay, such that at the output image we get a histogram which is equalized in the sense that given any kind of a probability distribution, okay, of the pixels at the input image, we are going to get an output image, or rather a processed image, in which the histogram of the processed image becomes a uniform distributed function, a uniformly distributed function. So that means to say that the probability of occurrences for all the gray levels are more or less equal. So that is one approach which we discussed, which we called as the histogram equalization. And we also discussed about the histogram modifications, in which case we took the original histogram of the image and we also defined a desired histogram of the processed image. And then what we did was that the original histogram, we made it, or we convert it into an equalized histogram, and from that equalized histogram we apply an inverse transformation that maps the equalized histogram into the desired histogram, and that technique we called as the histogram modification. Now both these techniques which we had discussed, there we were considering the complete histogram of the image. That is to say, if the image is of size n by n, okay, say n is equal to 256, so then 256 by 256 means it gives rise to 64k pixels. So over the entire 64k pixels, okay, we were defining the histogram. So the total count which we were getting, the total pixel count was equal to that 64k pixels, and the histogram was completely we can call those histograms as the global histograms, means histograms defined over the entire image. Alright. Now one point which should be kept in mind, that in an image, okay, we always find that the intensities happen to be different in different zones, okay, or rather even the distribution of the pixel intensities, that also changes from zone to zone in an image, okay. Let's take any typical image, like the image which we were considering in the last class. This is the original girl image, and there for different zones, alright, we are having different distribution of intensities. So what we can do, if we now, instead of constructing the histogram of this entire image, if we divide the image into some local partitions, okay, let us say that this is our image. Now what we are going to do is, this image we are going to partition into several zones. Supposing we make some zonal partitions like this, and then we consider all the individual zones, like let's say this consists of some n by n number of pixels, where n is sufficiently less as compared to capital N being the size of the image, okay. So we are considering a small zone, okay, and we are separating the image into several such small zones. Now what we can do, okay, is that instead of doing a histogram equalization over the entire image, that is to say, instead of considering the histogram of the entire image, supposing I concentrate on equalizing the histogram for individual partitions. So like say for example, I numbered this as partition number 1. Okay. And for partition number 1, I find a histogram. Supposing this is the nature of the histogram which I get for partition number 1. And on the partition number 1 only, okay, I apply a transformation such that this histogram gets equalized, okay. That is to say, we perform a histogram equalization, but not on the entire image, okay. We perform the histogram equalization on only this particular subsection, only on this partition of n by n pixels, small n by small n pixels. Then we consider this zone number 2, okay, and we take the histogram of zone number 2. Now the histogram of zone number 2 will be somewhat different. I mean, in general, histogram of zone number 1, which was this one, should be a little bit different from that of zone 1. So the histogram could be something like this, okay. The histogram nature may change slightly in zone number 2. And for zone number 2, again we apply our transformation such that the histogram is equalized. Okay. So the transformation which we are applying from zone to zone will not be the same, because the nature of the local histogram. So histogram of zone 1, I am calling as a local histogram of zone 1. This is the local histogram of zone 2. This is for zone 1, this is for zone 2. And the nature of the histograms, local histograms for zone 1 and zone 2 are changing. But we are equalizing every zone individually. Okay. And then we consider the zone number 3 and do it, and so on. So that means to say, for every such small partitions, we consider the local histogram and we equalize only the local histogram. Now, in this type of an approach, the advantage is that even if the image statistics, or rather the distribution of the intensities, are changing from zone to zone in an image, okay, we can effectively equalize, okay, the intensities, okay, concentrating on some smaller zones like this. So the quality of the image, okay, especially for those images where the intensities change rapidly from zone to zone, there, instead of a global histogram equalization, okay, we can do a local histogram equalization like this. So the approach which I just now mentioned, okay, that is to say equalization of histogram considering several local zones, okay, is known as local histogram equalization. This approach is called local histogram equalization, and the one which we had discussed in last class, okay, can be termed as the global histogram equalization. Okay. Now, very similarly, even the histogram modification of approach also can be defined locally instead of defining globally. So I am not going into that details. Okay, one can easily work out. Means the same philosophy of local histogram equalization can be utilized for local histogram modifications as well. All right. Now, today we are going to discuss about the spatial filtering of images. This is the topic for today, spatial filtering of images. Now, before we discuss this aspect, let us go over to the transformation function which we were considering in the last class. For the processed image, let us define the intensity as Vmn. I am writing Vmn as the intensity of the processed image, and I am writing the intensity of the original image, or rather the input image, as UMN. Okay, and we are applying some kind of a transformation function T, okay, over UN, such that we get the processed image intensity VMN. All right. In the last class, okay, I mentioned that this function T, this transformation function T, is defined, or rather this function T has got a domain of operation, okay, and that domain is usually a small neighborhood centered around the pixel under consideration. That means to say a small zone centered around this pixel Mn, okay. A small neighborhood area centered around this Mn is the domain of this T, okay. Or rather, a neighborhood region around Mn is considered in order to determine the pixel intensity at the position Mn for the processed image. All right. In the last class, I said that the domain of that neighborhood operation, okay, can change. The domain could be a small domain, it could be a very small neighborhood region, it could be a larger neighborhood region as well. Now, in the last class, what we considered was a very small domain, okay, or a very small neighborhood area, and we rather took the smallest neighborhood area, and that was what? That was a 1 by 1 space, okay. That means to say we considered only the pixel Mn. So the output, so for the processed or the output image, the intensity at the point Mn, okay, was dependent upon the intensity of the point Mn of the input image only, okay. It was not dependent upon any other intensities of other pixels, okay, surrounding Mn. So this operation where the neighborhood region was 1 by 1, we had called it as a point operation. Now right now, what we will do, instead of defining a point operation, okay, we are going to increase the neighborhood space of this function T, okay, slightly more. Let us say that instead of a 1 by 1 operation, we take a 2 by 2 operation or a 3 by 3 operation. Supposing it is a 3 by 3 operation that we do, okay, that means to say I apply the same transformation Vmn equal to Tu of Mn, but supposing I define that T, this function T, is a 3 by 3 neighborhood operation. If I define this to be a 3 by 3 neighborhood, then obviously V of Mn is not dependent on U of Mn alone. Can you tell me which are the points on which it will depend? It will depend on U m minus 1 n. It will obviously depend upon U Mn. It will also depend upon U m plus 1 n. It will depend upon U m n minus 1. It will depend upon U m n plus 1. It will depend upon U m plus 1 n plus 1. It will depend upon U m minus 1 n minus 1. Okay, and anything else? Obviously, I did not consider U m minus 1 n plus 1 and U m plus 1 n minus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 pixels, okay, and the value of Vmn is dependent upon the intensity values of all the 9 pixels, okay. Instead, I could have considered a 2 by 2 neighborhood operation, in which case I would have said it is dependent upon U m plus 1 n and umn or umn plus 1, um plus 1, n plus 1. That is to say, considering 4 points only in a 2 by 2 neighborhood. If I consider a larger neighborhood, a 4 by 4 or a 5 by 5, 6 by 6, 7 by 7, I can consider larger areas. Okay, but this is how the neighborhood operation will be defined. Now, the type of spatial operation which we will consider at first, okay, is what is known as spatial averaging. So, we consider that the intensity of the processed image, Vmn, okay, I define as follows. I define it as a double summation over a region KL, over a region W, okay, over a neighborhood region W, okay, and for this particular region, my index of operation is KL, okay, and see how I define the function AKL y of a minus k n minus L. Rather, what I am trying to do is that I take y of mn as the input image. All right, and I take, which I have already said, v of mn as the output image. All right, and W is a window, or rather a neighborhood region. All right, and AKL, this is a new term which I am introducing over here. AKL is nothing but a filter, or it's a filter of a very small size. Okay, it's a filter which is defined only over this window W. Okay, over a window W, I define a filter AKL. Okay, what it simply does is that this intensity, the intensity at the point m minus k n minus L is simply multiplied by this AKL term. So, what kind of a spatial operation are we doing? We are doing a two-dimensional convolution operation on this. Okay, just try to recollect our definition on the 2D convolution. What we are simply doing is a 2D convolution, and AKL, okay, define the filter's coefficients simply. So AKL are the filter coefficients. Okay. So what we are doing? We are taking the input image pixels and we are multiplying the pixels by their corresponding filter weights. Okay. And then we are summing them up. Summing up over what region? Summing up over a small neighborhood region, a small window W. Okay. So it is nothing but a weighted summation of pixels. What we are basically doing in this particular equation, okay, the physical interpretation of this equation is that we are doing a weighted summation, okay, over the window W. Okay, and by performing this weighted summation, I am computing the intensity value of the processed image at a point Mn. Okay. So since it is a weighted summation, I am doing some kind of a spatial averaging. Need not be an average in the true sense, but I am just adding up all the pixels. So this approach I will call as a spatial averaging. Okay. I think once I illustrate this with a very simple example, you will immediately understand that what exactly am I trying to do over here. Let us take some example. I take an image. The question is that how do we get the filter coefficients? We will come to that. Okay, we will be discussing about that. All right, let us consider a very simple case. Okay, I go back to this equation, and you assume that all the filter coefficients are equal to 1 over this entire area W. So that means to say AKL, consider that AKL is equal to 1, okay, over the window W. If I do that, then what am I doing over here? I am simply summing up the pixels, okay. And now if I consider that the total number of pixels in this window W is equal to NW, so N suffix W is the total number of pixels in the window W, okay. Then if I write VMN, I just take AKL equal to 1. In that case, I can just simply write KL belongs to the zone W, Y of M minus K N minus L, okay, and this entire thing I divide by W, okay, rather multiply by 1 upon W. If I do this operation, what am I doing? I am simply averaging over the particular window W, okay. Now in general, these AKLs need not be equal to 1 always, okay. These AKLs could be different, okay. But when AKL is absolutely equal to 1, then this is what we will do. Or I could have considered it this way, that instead of dividing this entire summation by NW, okay, I could have considered AKL itself as, I could have considered AKL equal to 1 by NW. If I had done that, then simply I could have written V of Mn equal to summation KL belonging to W and AKL. Obviously AKL is becoming 1 upon NW. It would have resulted in the same thing, M minus K N minus L, okay. Then I would not have considered any multiplication factor of 1 upon NW over here. So this is the spatial averaging operation, and let us see that how this spatial averaging is done, okay, over a window. Now I take an image like this. Okay, this is the input image, and let us say that this is the output image array. Okay. In case the grids are not very clearly visible to you, let me highlight the grids. And for the output image also, we are going to have exactly similar grids. Now, for the input image, I just have some intensity levels. Okay, so I just randomly choose some numbers. Okay, and I keep on filling this input image, assuming that that is my input image. Say I take the intensity values like this. Okay, like this, so on. Okay, I need not fill up everything. This is an image which is given to us, and I'd like to construct the output image after doing a spatial averaging. And let us say that my spatial averaging window size, okay, the size of W I choose as a 3x3 window. Okay, so a 3x3 window will be something like this. This is a 3x3 window which I have placed. Actually, this window is centered around this particular pixel, okay, which I am finding is having an intensity value equal to 7, okay, for this particular window. Now, what I do, I first start with the top left pixel. So, I consider this top left pixel first, okay, and my window center should be first positioned over here. So, I position my window center, okay, at this pixel whose intensity value is equal to 2. Now, one difficulty which I am finding, that this window is exceeding the boundary of the image. And mind you, this is a very typical problem which you are going to face in image processing operation. Okay. Now, what you can simply do is, a simplest solution which most of the times people adopt is that don't mind if your window exceeds the image zone. For the pixels which are non-existent, like this position, this position, this position, this one and this one, the pixels are non-existent. So, take their intensity values as equal to 0, okay, and then proceed. So, when the window is positioned over here, okay, what is going to be my local averaged value? 2 plus 4 plus 6 plus 7. So, 6, 12, 19, okay, and I am going to divide this 19 by how much? 9, because there are totally 9 pixels within the complete window. So, it is 19 by 9, okay. So, it comes to approximately 2 or so. So, I am just putting it into the nearest integer, so it becomes equal to 2. Now, let us position the window anywhere. Let us say that I am positioning this on this pixel, okay, that is to say whose intensity is equal to 7. So, I am circling this particular pixel and I positioned my window over here, okay. So, that means to say which pixel value am I going to determine for the output image? For the output image also I am interested in determining the pixel value for this point. Since I am interested in determining the pixel value of this particular point, I have positioned the window at the corresponding point in the input image. Now, over this window, I am just going to calculate the local average again. Can you tell me that what is the summation of all the pixel intensities over this window? 39. Okay. because it is 2 plus 4 plus 9 plus 6 plus 7 plus 3 plus 1 plus 5 plus 2, that becomes 39, okay. And since there are 9 pixels over here, okay, or rather the window size itself is 3 by 3 or 9 pixels within the window, it is 39 divided by 9, which comes to how much? 4, okay. So just see, in the original image, this intensity was 7, okay, and in the processed image, this intensity is becoming 4, okay. Now why this has happened? Because I somehow find that in the original image, okay, this 0.7, I mean suddenly I had got a pixel where the intensity value was equal to 7, but all its neighbors were, except for this pixel which is having an intensity equal to 9, all the other pixels were having relatively lower values, okay. So there is obviously an averaging effect which has taken place. Now if I want to determine the intensities over all the pixels in this particular image, what am I going to do? I will have to slide this window. So in order to determine the intensity at this particular point, which is having an intensity equal to 4, I position my window over here. Then for the next pixel, I position the window over here. Then this one. So like this, I will slide this window. So once the first row is over, I come over to the second row, position it here, position it here. I mean that's the point which I have considered. Then like this. So I will keep on sliding this window, and that's how I will get the average, okay, over the entire image space. Alright. So mind you, whenever I am considering a spatial averaging, it is always a point by point averaging which I am considering. So just imagine, just to calculate the output intensity at this point, I have to average over this 3 by 3 window pixels completely. Now if instead my AKLs were not equal to 1, what I would have done? Simply, supposing I take this particular example only, okay, that is to say my window is positioned around this pixel having intensity equal to 7, and let us assume that I have AKL equal to 1, okay, when K is not equal to 0 and L is not equal to 0. That means to say, I am considering AKL equal to something else. Let us say I consider that AKL is equal to 2, okay, when K is equal to 0 and L is equal to 0. If I consider AKL is equal to 2 when K is equal to 0, L is equal to 0, and AKL is equal to 1 otherwise, what I will be doing? I will keep on adding. I will multiply 2 by 1, 4 by 1, 9 by 1. So 2 plus 4 plus 9, 15, 6, 21, this 3, 24, this 1, 25, 5 makes it 30, 2 makes it 32. So the summation is 32. I haven't yet considered this pixel. This pixel is having a weight equal to 2 now, because I have considered that AKL is equal to 2 when K is equal to 0, L is equal to 0. Which is the K is equal to 0, L is equal to 0 position? The center of the window. So that is equal. So that is having an intensity value equal to 7. So I should multiply 7 by 2. So that means to say 32 plus 14 makes it 46, and the pixel intensity value becomes 46 divided by 9, or rather intensity value equal to 5. So this is a case where we are doing a spatial averaging, okay, but not an equal averaging. It is some kind of an unequal averaging, or rather a weighted averaging, where I can consider it this way, that my window was like this. My 3 by 3 window was such that all these coefficients were equal to 1, except for the center where the coefficient was equal to 2. Okay. I can consider many different mask size. I mean, I can consider, instead of considering a 3 by 3 masks, okay, I can consider a 5 by 5 mask, a 7 by 7 mask, 9 by 9 mask, I can keep on increasing my size. But can you tell me, or rather, is it possible for you to say something that if we keep on increasing the size of this window, okay, what is the effect that you are going to see on the processed image? Yes. Sharp conditions will not be there. Somebody said that the image sharpness will be lost. Somebody said that there will be an effect of blurring. Okay. Both the answers are very correct. As a matter of fact, wherever the sharpness of the image is missing, we call the image as a blurred image. Okay. So, what made you conclude this? Basically, you had concluded this because more and more you are inviting the contributions of the other pixels to decide the value of a particular pixel. So, if a particular pixel has got a high intensity, that means to say, if there is really a sharpness in the image, sharpness means an image which can correctly reflect the changes in intensities. Okay. If the change in intensities can be reflected very sharply, okay, we will call those images as sharp images. So, if there are such images where there is a good amount of sharpness, there are sudden changes of intensities, those images if you take and do the spatial averaging, what you are going to do? You are simply losing the sharpness. So, does it mean to say that the spatial averaging operation is bad? That means to say that, have we discussed something which is not useful at all, a spatial averaging? Because if it blurs the image, okay, definitely we have discussed something which is not of use. But can you tell me that what is the positive point of this kind of a spatial averaging operation? There is a low-pass filtering, and low-pass filtering, again, the reason is quite simple. It is a low-pass filtering because all the details or the sharpness of the images, those are getting lost. That is to say, wherever there are sudden changes in intensity, okay, all the sudden changes of intensities are getting smoothened out. All right. So there is a smoothening, there is a low-pass filtering effect, and obviously low-pass filtering gives rise to blurring. But at the same time, as somebody rightly said, okay, that it is also true that if we have some noise present in the image, okay, they will also get smoothed out, okay, during this operation. Okay. Let us say that supposing we position the window at this particular point and the intensities here are 354, 214, 213. Now this central pixel, I make the intensity as 11. It is not 354, 211.4, 213. So that means to say that suddenly this pixel has, I specifically earmark this pixel. So this particular pixel has suddenly a very high value. So it is a noisy pixel. There is some amount of noise, as a result of which it has suddenly become 11. And I apply my local averaging or the spatial averaging for this. Now what intensity value will it assume? 3 plus 5 plus 4, 12, plus 2, 13, plus 11, 24, plus 4, 28, 30, 31, 34. The total sum is 34. 34 divided by 9 makes it roughly 4. And if I replace this intensity of 11 by a value equal to 4 in the output image, okay, tell me, is the intensity value 4 is inconsistent with the intensity of its neighbors? It is more or less inconsistent with its neighbors, because its neighbors are having pixel intensities as 3, 5, 4, 2, 4, 2, 1, 3. 11 is something which is unusual. It's as a result of noise. But in the processed image, I have eliminated that noise, or rather I have reduced that noise. Alright. So spatial averaging is very good and it's very effective for noise reduction. Okay, and we can prove this mathematically as well. Okay, let us say that I represent the input image which I call as y of mn. Y of mn is the input image which I can write as u of mn, okay, plus eta mn, okay, where u of mn is, actually speaking, u of mn is the original image, or rather the original, I can say, noise free image, and eta of mn, okay, is a white noise, or rather a Gaussian noise which has been introduced on this pixel value at mn. Okay, so I have added an extra noise component to the original noise free image, okay, and made it a noisy image which I am calling as y of mn. All right, and assume that this white noise, okay, which I have introduced, is having a zero mean. So assume that the noise which I have introduced is a zero mean noise, and its variance you consider to be sigma square eta. Sigma square eta is the variance of this noise. Okay, and I have made this noisy image, I have created this noisy image which is y of mn, which is signal plus noise. Now I am going to do the spatial averaging on which image? Obviously on this y of mn. So on this y of mn I am going to do a spatial averaging, and in the process of spatial averaging what I am really getting is v of mn is the output image that I get, which is equal to 1 upon nw double summation, the expression which we had defined today only, index kl lying within w, u of m minus k n minus l plus eta mn. Okay, u of m minus k comma n minus l plus eta bar mn I am writing. Why eta bar? Because what is eta bar mn? It is nothing but the spatial averaged value of eta mn. So eta mn is the spatial average. It is the spatial average of eta mn. We are taking the spatial average of the image. We should take the spatial average of the noise also, because this noise is an additive noise. So if we have taken in this term, we have taken the spatial average of the signal, and in the second term I have considered the spatial average of the noise. Now it can be very easily proved that this eta bar mn which I now have, okay, what is going to be its mean? Its mean is going to be the same, that is to say, even eta bar mn is going to have a zero mean, but do you know what should be its variance? Since it is a sum of, since eta bar mn is the sum of all these noise terms, okay, divided by nw, okay, even the variance also will come down by a factor equal to nw. So I can write sigma square eta, okay, and I write sigma square eta bar. This whole thing I am writing as bar, indicating that this sigma square eta bar is giving you the variance of eta bar, okay, and that is equal to sigma square eta, where sigma square eta is the variance of eta mn. So this is nothing but variance of, this is the variance of eta, this is the variance of eta bar, and this variance sigma square eta divided by NW. So what happens? The variance comes down, okay, or rather the noise power comes down, okay. So the noise power reduces by a factor NW, okay. So as a result of that, the signal to noise ratio, okay, or rather which we call as the SNR, the signal to noise ratio goes up by a factor NW. Is that clear? So obviously we are reducing the noise. But at the same time, as somebody was saying, that if we do the spatial averaging more and more, definitely it results in blurring. That means to say what? Even the genuine details of the image will also get smoothed out. Okay? And let us see some results from which it will be clear that if you over smooth something, okay, what kind of problem does it result? Now, I consider an original image. This is the original girl image, okay, which you had seen in the last class also. And what I have done, using a computer, I have added some noise to this image, okay. So the noise is something like this. If on this image, okay, I just take a container of salt and a container of paper, and if I keep on pouring the salt and the paper, okay, into this image, okay, the image that results, okay, is definitely going to be a noisy image. Noisy image because some of the pixels will be corrupted. Some will be corrupted with salt, that means to say its intensity will suddenly go up, and some pixels will be corrupted by the paper, that means to say their intensities will drastically come down. So I have just added the salt and paper noise, and this is a kind of image that I have got, okay. I'm not sure whether you can clearly make out. Of course, if you are concentrating on some specific regions, you will find that there are some bright spots occasionally, and similarly there are some areas, possibly in this zone, where you will find that there are some isolated black spots as well. So you can see some isolated spots present in this image. So this is, I can say, as a noise corrupted image. And we have generated this noise corrupted image using a computer. Alright? And then what we have done, we have applied a local averaging, okay, over a 4x4 window. So this is 4x4 window. Over a 4x4 window, I have applied a local averaging, spatial averaging. Just see, there is, what are you seeing? Firstly, that all these occasional noisy pixels which were there, they are no longer present, okay. But at the same time, as compared to the original image, there is definitely a loss of sharpness. Can you make out? There is definitely a loss of sharpness which has taken place. Now, if instead of 4x4 window, I increase my window size to 8x8, what kind of a result do you expect? Further blurring. Already noise reduction is there, but even if there is some amount of noise at this stage, okay, there will be further amount of noise reduction. But of course, a further blurring should take place. And see what kind of an image it is. Can you make out anything? It is after 8x8 local averaging. This is the way we normally look at any out of focus image, okay. If we have a completely out of focus picture somewhere, Those kind of images will look like this. And we have got an image like this simply by doing an 8 by 8 local averaging. Alright, so this is one type of a filter which we had seen, where the primary use is for the reduction of noise. Okay. Now, we are going to see yet another kind of filtering, okay, which is also useful for noise reduction. But in this case, the filter which we have just now discussed, is it a linear filter or a non-linear filter? It is obviously a linear filter, because we are summing up all the, or rather we are doing a weighted summation, and we are summing up everything, dividing it by 1 upon NW. So it's definitely a linear filtering which we have done. Now I'm going to discuss a technique which is absolutely non-linear. And the operation is like this. I'm considering the pixel intensity for at the point Mn. So I'm considering V of Mn. Okay. And I define V of Mn as follows. I define V of Mn as the median value, okay, over Ym minus k n minus L, okay, where as before the KL indices are for the window W. I again choose a window W centered around, okay, this Mn pixel, okay, and I call the index of this window parameters as KL, okay, and over this window I consider the median value. I think all of you are knowing what is a median. Let me just illustrate this with an example. Supposing I consider a window like this, a 3 by 3 window, and for this 3 by 3 window, supposing the values which I am having is 1, 2, 5, 18, 4, 3, 2, 7, 5. Now, what is the, if I now write all these intensities in the ascending order, okay, what does it result? 1, 2, 3, or rather 2, there are 2. So 1, 2, 2, then I write 3, then 4 is there, 5, there are 2 pixels, 5, 5, okay, and then I have 7, and then lastly 18. So I have just sorted all these intensity values in a non-decreasing order. So this is sorted in intensity values, sorted in non-decreasing order. Non-decreasing because it is 1, 2, 2, okay. So like in this case 2 pixels are having the same values, again 5, 5, so 2 pixels are having the same value, so it is non-decreasing.
We can call it increasing.
Well, increasing, some books and literature, they are, very cautious. They say that you can call it as an increasing sequence, okay, only when the kth plus 1th element is higher than the kth element, okay. So let us be safe and call it as a non-decreasing order. So how many pixels are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 pixels. Now what is going to be the median? The median is, okay, out of these 9 samples, the median will be exactly the sample which is appearing at the middle, okay. So this one. So there are 4 on this side, 4 pixels on this side. So this 4 is the median value. So what am I going to do? I am going to replace this pixel with 4. Of course, in this example it is already 4. But supposing if I had got 4 over here and 18 over here, meaning if instead I would have got this as 1, 2, 5, then I would have got 4, 18, 3, 2, 7, 5. If my mask would have been defined like this, then what would have happened? Again, Median filtering means in the non-decreasing order I would have arranged it like this only, okay, and median would have been still 4. So I would have replaced this pixel value of 18 by a value equal to 4. And just see what I have done effectively. Again, this pixel intensity value of 18 is definitely a noisy pixel because it has got no relationship with the other pixels which are present in the image. Okay. So again, for the median filtering also, we are going to do a very similar thing. So, like say for example, if this is my original input image, all right, I am going to consider a window like this, okay, which I am going to slide, okay, and this output image, of course, this output image I was generating by local averaging, but this time I have to generate a new output image, okay, by median filtering. But so simply what I do, if I position this over here, okay, over this circled pixel which is having a value equal to 7, okay, what is going to be the median filtered output? The median filtered output is going to be 4, okay. In this case, luckily the median filtered value and the spatial average value becomes the same, but in general it will not be so. So median filtering is also good for noise removal. But tell me one thing, that if I have two sequences, okay, and one sequence is x of m and the other sequence is y of m, and then if I have median of x of m plus y of m, okay, is it going to be equal to median of xm plus median of ym? So it is not. So this is a non-linear operation. All right. So we are going to consider the median filter properties and the other type